Alright, the next one here is going to set up a situation where there's both tension and shear on a bolt. What I'm going to draw out real quick is just a sort of pillow block bearing. We worked a problem that only had tension loads in it with a similar geometry once before. This is something geometry-wise similar. I'm just going to load it in a little bit of a different direction here. And it doesn't make a whole lot of difference what it looks like from this point. So you got some bearing joined to a plate. There's two bolts, one centered right there, one centered over here. We'll give dimensions here of 20 millimeters. Let's call that 60 millimeters, and we'll make this also 20 millimeters. So a little bit rough notation there, but basically 60 millimeters between the two bolts, and then 20 millimeters from the bolt hole to the end of the plate in both cases. Now this one I'm only going to load the pillow block with a horizontal force. The last one was purely vertical. This one's horizontal. Call it 1200 newtons. And I'm going to need the spacing off of the bottom of the plate for that, which will be all the way down. No, it's not cooperating here, but it'll be all the way to the bottom of the plate there, that full distance. Working pretty good today. So there we go. That is 45 millimeters. The assumptions that we're going to make here that the plate again is rigid, which once again means that as it deforms, it just transfers load between the two bolts directly. Now we're also going to have to assume that the plate essentially rotates about some point. We're going to take that point as right here. So as it rotates about that point, it's basically stretching both of the bolts due to the moment created, since that 1200 Newton load is offset. So we'll say that the forces in the bolts, I'm going to add a word in here, the tensile forces. Are just proportionate to how much they would stretch under the above assumptions. We assume I put stretch in quotes because what I'm really talking about is strain, but there's no need to go into a strain-based definition here. So really what we're looking at is this plate is rigid, then that 45 Newton, or excuse me, that 1200 Newton load is wanting the plate to sort of rotate upward away from that point right there. I'm going to call that just point P so I have a reference for it. So as that stretches, each one of those bolts gets stretched by some amount. And since the plate is taken as rigid, it's a direct proportion of the lengths. So if this is 20 millimeters and this is 80 millimeters out to there, then the force ratios, if I call this FA, this FB, FA, just you can run through the triangles here, the actual stretch of FA is going to be 4 times the stretch of FB because 80 is 4 times 20. So we can say from that alone that FA is 4FB. So all we're doing there is using that proportionality assumption to form a relationship between the load and the two bolts. To actually calculate those values, what we can do is we'll add back in the actual force, keeping things in their original orientation. Keep wanting to call that 45. That's 1200 newtons and a 45 millimeter offset. So what I can do now is sum moments at P. Take in either direction to be positive and set it equal to 0. So I'll have 1200 times 45 minus FB times 20 minus FA, which is 4FB, times 80. And I can solve that now for FB. .8 newtons. Now this again assumes that those bolts are of the same diameter. The amount of stretch relative to the two bolts would be the same regardless of diameter, but the actual force generated would change if they were not the same diameters. But here we're just going to assume that they are. So FA is equal to 4FB, and I should point out this drawing here, that amount of rotation is drastically exaggerated. In practice, you would never actually see the thing rotate. It's just the proportionality of it that I'm exaggerating there to make this clear. So in reality, we'd be talking about very small rotations. So what this means relative to a free body diagram, I'm just going to roughly represent this. Means we'd have two tensile loads acting here at FA and FB. FB we just showed to be 158.8. FA is 4 times that, or 935.3. And then we've also got, since this 1200 is in the x direction, that has to react somewhere as well. And at that point, you've got to make a sort of decision of, do I want to assume that that shear load is carried by friction, or do I want to assume that it's carried by the bolts? We're just going to assume here that it's carried by the bolts. So on each of these bolts, remember the assumption for that is that it's split evenly among all of the bolts carrying shear, so each one will just carry 600 newtons. Now at this point, it's well worth pointing out, so each one of these represent the forces on the bolts. These are sort of in the y direction, the 600 newtons are in the x direction. However, in calculating stresses from these, the 600 newton, that causes a shear stress. It's a direct shearing stress relative to the bolt, so that would be an F over A type of calculation, where A is based on the full shank diameter of the bolt. Now I've got an error here. This should be a 635. So the 635.3 and the 158.8, those are tensile loads. Those are loaded along the axis of the bolt, so those cause axial stress. Now in terms of calculating stress, we've got two possibilities. If we think about the actual joint here as two plates coming together, got the bolt going through, it would be typical, that's your shear plane, the interface between the two, it would be typical that at the shear plane you use the full bolt diameter. Okay, so if this was a 20 millimeter bolt, you'd base the area on which you'd calculate the shear as F over 20 millimeters. If, on the other hand, you were shearing the bolts, that's a whole different thing. We kind of hinted at this in class. If you put the threads of bolts in direct shear, the interaction becomes much uglier, because you're putting direct bearing stress on threads. You're putting the joint itself into bearing stress on threads, and there's a big stress concentration there as well. So you would typically want this to be true. If that's the case, then you can then calculate this axial stress at the full bolt diameter as well for that location on the bolt. But somewhere else on that bolt, that threaded bolt, you've got the thread diameter too. So for what we're getting at is at the shear plane, you'd use the full diameter calculate both sigma and tau. Away from the shear plane, tau is going to be 0 because you're only applying shear forces directly on that plane. There'd be some effect a little bit above and below the shear plane, but it's only a maximum at the shear plane, and any sizable distance away from it, it's going to be 0. So tau is 0, and sigma can be based on AT. That's where it's going to be a maximum. Remember that the area AT is always smaller than the full bolt diameter, the full shank diameter. So that tension is carried throughout the full bolt. It's carried throughout the threaded portion, and it's carried throughout the non-threaded portion. The stress it causes is always going to be higher in the threaded portion. But since you typically don't put the threaded portion on a shear plane, you got to keep that difference in mind. That at the shear plane, you're going to calculate both sigma and tau based on the full diameter. Away from the shear plane, your true maximum sigma will be based on AT.